This second lecture on axiomatizability is a direct continuation of the first one. To begin with, I want to complete the discussion of general theorems on axiomatizability with a remark, and then I want to cover the following topics, which will not be covered in a completely detailed way, but I certainly want to comment on the most important results. First, after the remark, we'll talk about finite axiomatizability and consider a number of positive examples. Next, axiomatizability by universal sentence. Here we'll be interested really in negative results, and when we would expect to have a positive result, in fact, we can't get it, and we'll want to discuss the way in which one can prove such a negative result. It's characteristic of such logical investigations that one expects in many cases to obtain rather decisive negative results about the possibility of a certain kind of axiomatization. The next topic, which I've labeled 4 here, is to extend the discussion in terms of axiomatizable by a universal sentence to the more general case of finite axiomatizability. So we would have now the possibility of existential quantifiers, and the technical considerations in proving negative results are certainly more complicated and more difficult. The proofs are quite tedious at this stage. We'll want to talk about some of the results. And finally, a topic of special interest in measurement, we want to look at the problems surrounding characterizing the Archimedean axiom within elementary theories. So that's the agenda for this lecture, and we should have time to say what is important about each of these topics. Now, to complete the discussion of general theorems on axiomatizability, I want to end with a positive remark which is formulated in the chapter in terms of a theory. It's natural to ask, when might we get some positive results that are easy to state? And one answer is that we can get a recursive axiomatization. I won't state the theorem exactly, but the basic idea is quite straightforward. Whenever the numerical relations and operations of the embedding numerical structure of the class of measurement structures, finitary class, let's say, when those operations and relations are definable in terms of addition and numerical addition and equal to or greater than. For example, certainly addition and equal to or greater than. If we had a finitary system of extensive measurement, it would be so embeddable, because the operation of combination in the extensive measurement would correspond to addition, and the ordering would correspond to equal to or greater than. Now, the logical result applicable here is that it was shown many years ago by Pressburger that the elementary theory of addition and equal to or greater than as a numerical theory, the variables just ranging over numbers, that theory is decidable. Means that there is a mechanical procedure, a recursive procedure for deciding whether any given sentence of the theory is valid or not. That result can then be used in a fairly straightforward way to give a recursive axiomatization of theories that have this definability in terms of numerical addition and equal to or greater than. All right. What we want to turn now to are much more particular results about theories of measurement. And first, we want to consider problems of finite axiomatizability. Now, for the results already stated in the general theorems and results we've hinted at, we'll finish discussing with the discussion of the Archimedean axiom. It's clear that we're not going to get interesting results on finite axiomatizability when the models are infinite. We need, from the standpoint of elementary theories, to have interesting positive results and in fact interesting negative results, really, to restrict ourselves to finite models. And let's first consider several examples from Volume 1 that show that there are standard finitary theories of measurement that are finitely axiomatizable. The first example would be finite weak orders. Notice that when the models are finite, we only have two axioms, namely connectedness and transitivity. Notice, of course, that when we remove finiteness, as we discussed in the lecture on ordinal measurement, the story is very different. Then we must impose a non-elementary condition, the existence of a finite or countable order-dense subset. And that condition is not elementary and we cannot get a finite axiomatization in an elementary theory for the infinite case. But the finite case is so simple, it's indeed trivial. We also give in Volume 1 of Foundations of Measurement a number of special cases that are of interest that have very simple axiomatizations. And these cases are those in which we have equal spacing, finite and equal spacing, as in the case of the finite equally spaced conjoint structures, or also the finite equally spaced different structures, both of which are discussed in Volume 1 in detail, and the representation and uniqueness theorems are proved. An important point, by the way, about these three cases I've just mentioned is that not only do we have finite axiomatizability, but we're axiomatizing structures that have very nice uniqueness properties. Of course, it's very crucial to realize that in the case of these finite conjoint structures and finite different structures, the particular finite structures characterized by the axioms are very special ones, namely when we have this beautiful symmetric property of equal spacing. Now, the situation is a little more complicated with another example discussed in Volume 1, namely finite probability structures in which the atoms, the events at atoms, are all equivalent in qualitative probability. So they'd all be assigned the same numerical probability in the representation. And that example also applies to equally spaced extensive structures. The difference that comes into this example that makes it have a feature not in the first three examples I've discussed is that in the axiomatization given in Volume 1, we automatically assume that we have available the standard elementary set theory. But that's not part of the elementary theory. Remember, in the elementary theory, we just have objects ranging over, variables ranging over one kind of object intuitively, and we don't have stated as axioms the axioms on set theory, elementary set theory, required to make it an elementary theory. But that is not a difficult change. It takes a number of elementary axioms, but the way to do it is to axiomatize the Boolean operations directly. Operations and, if we want, the one relation of ordering. And so we need to introduce as the non-logical constants in finite probability structures, now looked upon, axiomatized as an elementary theory with finite axioms. We need to introduce Boolean union, the axioms for Boolean union, Boolean intersection, Boolean complementation, a constant for the Boolean universe corresponding to the set of objects in the original formulation, and the Boolean empty event. And as usual, then the qualitative ordering. Notice that in the original formulation, because we'd assumed the set theory, the only new primitive we introduced was the qualitative ordering, really. Now we have to have these other primitives to characterize the elementary operation on sets. And in the chapter, we have a formulation of that in terms of 18 axioms. Those axioms constitute really primarily a very straightforward axiomatization of Boolean algebra, plus what is needed for the qualitative ordering. And we'll not state them here. But it's an important example to show how what would appear on the surface maybe not to be easily put in the form of an elementary theory with finite number of axioms can be so transformed. Now, these are not the only examples of importance. In the 2 lectures on geometry, some other examples were introduced. Now, notice, of course, an important point here. A typical case would be the axioms introduced for the Desarguesian projective plane. And if we want to add another axiom, with Pappus's proposition satisfied. Now, if we reflect on what was done in the chapter and in the lecture, the models of the projective plane are certainly not finite. But on the other hand, I'm saying we have finite axiomatizability. Well, the reason is that we are not really axiomatizing this in a way that makes it a theory of measurement structures. The reason being that, if you'll remember, the representation, the general representation, is over an arbitrary division ring, not a division ring of the real numbers. Consequently, in saying that we have finite axiomatizability in these geometric examples, we are weakening our requirement about measurement structures. And that's important to realize, that restriction has been eliminated, and not one that we're going to deal with in the rest of this lecture. And I only mention it as an example where we have finite axioms, a finite axiomatizability, even though it's not the kind of measurement example we're primarily interested in. On the other hand, it is important to realize that the axioms are elementary in the case of the projective plane. Now, to continue the discussion of finite axiomatizability, we now want to go from the positive to the negative, so to speak. Namely, I want now to turn to negative results, and we'll do that first by restricting the axiomatizability tools available to us. Namely, we'll restrict ourselves to axiomatizable by universal sentence. Now, it's worth saying something about this restriction. One way of thinking about it is as follows. When we introduce a theory of measurement, and let's, for the moment, restrict ourselves to finite models. If we have a model M that's a measurement structure, take the case of orders, then it's very natural, if we have some model M prime that's a submodel, to think that M prime should also satisfy the axioms. That's in the general case. Order is a very nice example. Another simple example would be semi-orders. So, associated with the property of being closed under submodels is a very natural relation to axiomatizable by universal sentence. In fact, we have, as a first result to state, a theorem of Tarski's from 1954. Namely, if an elementary theory is finitely axiomatizable and it's closed under submodels, then it is axiomatizable by universal sentence. So this shows why it's very natural, if we think of measurement theories having the property that the models are closed under submodels in the empirical cases of interest, why it's natural to think of axiomatizable by universal sentence. This theorem of Tarski's gives us an exact formulation. If it's finitely axiomatizable and it's closed under submodels, then we have this universal sentence property. Now, unfortunately, the situation as expressed in Tarski's theorem is not as simple as we extend it to finite models as we would like. Remember, we know that we're, for theories of measurement, not mainly going to have finite axiomatizability in an elementary sense for theories of measurement, just because of the problems we discussed of the Lowenheim-Skolem-Tarski theorem. So we're mainly talking about finite theories, finitary theories, that is, finitary classes of measurement structures that we want to axiomatize. Now, a natural conjecture that extends in what would seem to be a fairly intuitive way Tarski's result is a conjecture that Scott and I made in 1958. in connection with some other results we obtained. The conjecture was that if, when a sentence is satisfied by a finite model M, it is satisfied by every submodel of M. So I have the property I've discussed about here, except we're restricting ourselves to M being a finite model. So M, let's say now finite, and the property that any M prime contained in M, then the sentence satisfied in M prime as well. Suppose a sentence has that property. Then we conjectured there is a universal sentence finitely equivalent to the sentence. And by finitely equivalent, we simply mean two sentences are finitely equivalent when they're satisfied by the same finite models. Notice that that extends Tarski's result, or to the condition now not of being satisfied by submodels in general, but by a restriction on finite models, which is what we're interested in. Now, unfortunately, William Tate showed a year later in 1959 that this conjecture that Scott and I made is false. And we want to examine later the nature of Tate's example, if we have time, because it shows what some of the problems are in passing from axiomatizable by universal sentence to finite axiomatizability. Now, let's consider another kind of example, very familiar in measurement, that shows why it seems natural to think about axiomatizable by universal sentence. Suppose we have a structure M that is a different structure. Let's just take, for the purposes here, the relation is represented numerically. It corresponds to algebraic difference. Now, if we have a set of objects, finite now, finite model of, in other words, a set A and a quaternary relation D, so that we can embed D in this standard numerical relation. Remember, the set A is finite. And we have no other restrictions on D. Then it's very natural to think that this must be closed under submodels. And it's very natural, therefore, being closed under submodels, to expect the axioms to be possible to state axioms in the form of universal sentences. Because if we take, if for example, we have some existential axiom, there exists an A, say, with a certain property, such that for every B, so-and-so, and now, in the model we originally considered, A is eliminated in the submodel, then of course that existential axiom might not hold. But if it were universal, it certainly would hold, because the variables range over all objects in the set A, and consequently will automatically hold under submodels. Notice, it's obvious, and we haven't stated it, but it's an obvious property of a sentence, of a universal sentence. If it is satisfied, if a universal sentence is satisfied by a finite models we're talking about now, then it's satisfied by any submodel of the finite model. Our problem is going the other way, is where the difficulty is. So, what I want to emphasize, though, is that the intuition back of studying when an elementary theory is axiomatizable by universal sentence is a natural one for a whole class of measurement structures. Namely, as exemplified here in the case of difference, when we take finitary class of measurement structures closed under submodels, we would think that we should be able to characterize it in terms of a universal sentence intuitively. And so it's worth investigating when we can do that. Now, fortunately, using some earlier results of Bob Vaught's, Scott and I, back into the 1958 paper I referred to, were able to state a criterion we called Vaught's criterion, for a finitary class K of measurement structures. Remember, finitary means the models are finite. For a finitary class K of measurement structures to be axiomatizable by universal sentence. And this criterion of Vaught's is very nice. Now, there is one restriction in the hypothesis we want to be clear about. We do not have in the elementary language any elementary function symbols. So we're dealing with essentially just with relations. Notice function symbols create a problem in terms of closure properties. So, according to Vaught's criterion, a finitary class K of measurement structures with respect to some elementary language L that has no function symbols is axiomatizable by universal sentence if and only if the following two conditions are satisfied. First, K is closed under submodels. Second, there exists a positive integer n such that if any finite model A of L has the property that every submodel of A with no more than n elements is in K, that is in the finitary class, then A must be in the finitary class. And it's that having a fixed n. So that's the order the quantifiers notice. There exists an n such that for every finite model A. And it's that second condition that has the power in it. Let's take a positive example of that condition to understand a little better. Take the case of weak orders. Now, we know weak orders are axiomatizable by universal sentence. We just take the conjunction of connectedness and transitivity. What is the value of n for weak orders? N is equal to 3. And notice, n being equal to 3 is just the same as the number of distinct variables in the axioms. The number of variables in particular we need to formulate transitivity in the case of weak orders. When we're axiomatizing by a universal sentence, the number n will be closely related to the number of distinct variables in the axioms. And a way of saying intuitively what's going on is that if we can axiomatize by a universal sentence, and that's a fixed universal sentence, that fixed universal sentence must have a fixed number of distinct variables. And that fixed number of distinct variables really tells us what n must be. Whereas if there is no such n, if to characterize when such models A are to be an element of K in terms of their submodels, we have to keep expanding the size of the submodels to consider so that we intuitively require an unbounded number of distinct variables to formulate the conditions. Then it's clear intuitively that we're not going to have axiomatizable by a universal sentence. The theory will not be so axiomatizable. Now, this weak orders provides a very simple example. A good exercise is to look at some other cases. For example, semi-orders as the next case, and to ask what n is, and other cases that will occur to you. What I want now to do, however, is turn from consideration of such simple positive examples in which being axiomatizable by universal sentence holds to negative results. What we want to do is show, construct models, a sequence of models really, to show that Vaught's criterion cannot be satisfied, and therefore we cannot have the theory in question, that is the finitary class K of measurement structures, axiomatizable by a universal sentence. To get negative results using Vaught's criterion, it is natural to state a corollary that is just its negation. And let's examine that, because we'll use that in the examples we want to consider. So, under the hypothesis stated before about K being a finitary class of measurement structures. K is not axiomatizable by a universal sentence if and only if, for every positive integer n, there exists now a finite model A of L, such that every submodel with no more than n elements is in K, but A is not. That's a very simple transformation of Vaught's criterion for a negative application, showing something is not axiomatizable by universal sentence, and it's the form we will use. Now, let's consider two examples. The first one is, in many ways, a particularly surprising one. That's indistinguishability. In a way, this relation is the one that doesn't hold when we have a semi-order, so two objects are not separated by just noticeable difference, put intuitively. They're indistinguishable. That relation, of course, is not transitive. It's not an equivalence relation. The representation says we intend by this equivalence relation, by this indistinguishable relation, a numerical representation of the form the absolute value of f of x minus f of y is equal to or less than 1. The choice of 1 is irrelevant here. We could take any other positive real number as the constant in the representation. And Fred Roberts proved in 1968 that we could not axiomatize by a universal sentence this indistinguishability relation for finite models, and the proof just shows you can have cycles of length n that don't satisfy it as required here, and all the n minus 1s do. Or another way, that for every n we can get at that. But all the submodels with no more than n elements are okay, but with cycles greater than n, the indistinguishability cannot be properly numerically embedded. Now, that example, though it's surprising, given how simple semi-orders are, and there's more structure in semi-orders than in just the indistinguishability, it shows that there are subtle problems here in axiomatizability questions. That example is not as interesting from a straight measurement standpoint as the next one. Namely, I want to discuss the proof in it more care. I didn't want to go into the proof in the Roberts case because I don't want to get into the language, the graph theoretic language, to make the proof really explicit. The second example is different structures, and this result goes back to the 1958 article by Scott and me. Now here we're considering finitary models again. We have the class K. A is a finite set always, and D is the quaternary relation of algebraic difference. The numerical relation in which we embed all the members of the finitary class we'll call delta, where delta is just what I was discussing earlier, xy delta uv, if and only if x minus y equal to or greater than u minus v. And what we want to show is that we can apply Vaught's criterion to establish that we can't have axiomatizability by a universal sentence. And notice I already discussed just a few moments ago how intuitive it is to think that should be doable. Because if we have this closure under submodels, we would think we'd be able to capture the requisite properties. The point about the proof, and the proof will show this, is that what happens in these kinds of cases, it also happens in indistinguishability, is intuitively the complexity of the models is unbounded. As the number of elements in the models increases, the relationships that have to be expressed explicitly between the elements of the model is unbounded in character. Now, it isn't really desirable here to give the full proof for each end, showing that for every positive integer n, we can find a finite model that has the property that every submodel with no more than n elements is in K, that is embeddable in the numerical relation with delta, Re delta, Re the set of reals, and delta as a numerical relation, but that A itself is not. But the method of proof can be seen explicitly from the construction of a 10-element model. This 10-element model will have the property that it cannot be embedded in RE delta, that is the numerical structure, but that any submodel, 9 elements or less, can. So let's examine. I've drawn here a little picture of this 10-element model. We have on the right-hand side A1 to A5. Then we have what is intuitively meant to be a big interval, gamma, and then A6 to A10. And the trick here is to make the interval alpha, going from A1 to A5, intuitively equal to beta, going from A6 to A10. And if everything were appropriate numerically, alpha would be the same as beta. But now our trick is the following. First, we separate these two so that we stay out of problems when we drop an element by making gamma strictly greater than either alpha or beta. That's part of our relation. Then we also have a subinterval comparison between the alphas and the betas. The alphas are, notice, the small intervals, atomic intervals on the left-hand side, and the betas are the atomic intervals on the right-hand side. Now we assume alpha 1 is equivalent in size to beta 2, that's all qualitative, alpha 2 to beta 4, alpha 3 to beta 1, alpha 4 to beta 3. And notice the trick here is that if we add, what we have to avoid here is being able to add these up elementarily so that alpha must equal beta. Because what we're going to assume is, in addition to these equivalence relations, that alpha is less than beta. So that obviously there can be no numerical embedding of the full model, because you couldn't have these equivalence relations and at the same time alpha less than beta. And notice the construction here, which we generalize to arbitrary n, has a certain salient quality. If we add on the left alpha 1 plus alpha 2 that are adjacent, we cannot add adjacent intervals on the right to get a larger interval. So we can't add beta 2 and beta 4 intuitively because they aren't adjacent. And correspondingly, beta 4, beta 1, beta 1, beta 3. And so we block building up to, in the obvious way, alpha equal to beta. And now what we can show is that by just this one relation, alpha less than beta, violating the numerical constraints, that is no problem if we drop any one of the 10 elements. So if any one of the 10 elements, then the model consisting of what I've shown here, gamma strictly greater than alpha beta, these relations, and alpha less than beta, can be shown to hold, and to be embeddable. Hold means be embeddable in the intended numerical structure. And that kind of construction is very typical of the way in which we apply a Vaught's criterion. That we can start with something that's a proper numerical model, but have the relationships just so that we can destroy, that is, turn around and negate one relationship, and negating that one relationship will not affect the numerical embedding of any of the submodels, but will, of course, destroy the possibility of embedding the full model. So that gives us a negative result for difference measurement. Now, given that result, it's fairly direct to get then a negative result also for conjoint measurement. Notice what I mean by a negative result. If we define the finitary class of conjoint measurement structures, we cannot axiomatize that class by a universal sentence. That's what a negative result means. And the method of argument is very similar to what we've given for the difference case, as you would expect given their closeness. What is interesting is that we can also generalize these results with a little care, as Tateev showed in 1972, to a corresponding negative result for finitary classes of measurement structures that we want to embed in n-dimensional space with the Euclidean metric. It's very important to T's result to stress that we're talking about the Euclidean metric. Tateev has shown that in other special cases one can get similar results. But for example, if you take the familiar city block metric, he has results for low dimension, but it seems to be very complex to get a general result for arbitrary n. This result for the Euclidean metric, a nice thing about it is it holds for n dimensions, for any finite dimension. And again, what it shows is that with Euclidean metric, the relations are going to be sufficiently complex that as the number of elements in the model, in the finite model, builds up, we can't express those in a uniform way by a single universal sentence. Now, as I said, the conjecture that Scott and I made that we could prove the equivalence of this not being axiomatizable by universal sentence when we had closure under submodels to finite axiomatizability, that conjecture was shown to be incorrect by Tate. I don't really have the time to go into Tate's example. It's explained in detail in the chapter, but it is a fragment of elementary number theory. Looks like a piece of the elementary piano axiomatization practically, and you'll find it interesting, I think, to look at. It shows, Tate's result is that he has the property, this elementary fragment of number theory, that it's not axiomatizable by universal sentence, it is closed under submodels, and it has a very simple finite axiomatization. Well, given Tate's result especially, it then is of interest to ask, what about these cases of interest in measurement? Tate's counterexample is not in itself of interest in measurement, but in the case of difference measurement, conjoint measurement, or the multidimensional scaling example with Euclidean metric. What about these examples when we now ask, well, we can't have, as we've shown by the arguments and methods just discussed, axiomatizability by universal sentence, but maybe we can have for these finitary classes of measurement structures a finite axiomatization. Well, by deeper and more complex methods, using especially arguments given by Per Lindström of Sweden, which haven't been published but are in the chapter, we can show that the results just stated for different structures, for conjoint structures, and for multidimensional scaling structures with Euclidean metric, that these examples, same negative results, extend to finite axiomatizability. That is, we cannot have a finite list of axioms that will work either. I'm not going to discuss the methods of proof. They're rather intricate and involve more logical developments than it's appropriate to try to cover in this chapter. Those who are especially interested in detailed and deeper results about axiomatizability, I strongly encourage to have a look at that section of the chapter. Now, the final topic that we want to discuss is the Archimedean axiom. Notice how important it is to have some discussion of the Archimedean axiom in an analysis of axiomatizability. Because if we examine the measurement structures that we've considered in Volume 1 and in many parts of Volume 2, some form of an Archimedean axiom is needed, really, as we have said, whenever the models that we're especially interested in are infinite in character. That is, the domain of the models is infinite. And it's natural to ask, given the fact that on the surface the Archimedean axiom is not elementary, remember, it always involves something more in its formulation than simply quantifiers ranging over the intended empirical objects. It's natural to ask, well, can we replace that axiom by some class of elementary axioms? And the result is that an emphatic no is the appropriate response. And that's an important result, for it shows that when we want the characteristic structure for infinite models that we have asked for in the case of measurement structures, of embedding in the real numbers under an appropriate structure, we cannot characterize any of these models satisfactorily as elementary theories, because we cannot formulate the Archimedean axiom or its equivalent by any collection of elementary sentences. So in this sense, we have a strict result about not being axiomatizable in an elementary way in any form at all. Let's state one theorem. There are really two theorems that we want to consider here. The first one is, let the class K of models of an elementary theory T in elementary language L satisfy the hypotheses of the earlier theorem, where we had two assumptions. One is that some of the models in K are infinite, what we're always interested in. Two, in this case, that the theory of weak orders is interpretable in T. So the theory is rich enough to provide interpretability of T. For such a theory T, there is no set of elementary formulas of L equivalent to an Archimedean axiom for T. And the proof of this just applies the earlier theorem, which itself relied upon using the standard Lowenheim-Skolem-Tarski theorem about infinite models. If one has infinite models of one cardinality, one has infinite models of every infinite cardinality. So in this sense, this negative result is quite general. In the case whenever we have the kind of order theory we expect to have, then we can see from this theorem it's hopeless to have any sort of formulation that gives us in an elementary way the equivalence of the Archimedean axiom. It is, in fact, this kind of result that has justified, in many respects, the kind of general set theoretical formulation for axioms that we've used throughout Volume 1 and 2. And why the interest of elementary theories and elementary axiomatizations in the sense of elementary languages is pretty much restricted to finitary classes of measurement structures. The second theorem about the Archimedean axiom is a simplification of some results published by Narrens in 1974. And the virtue of this theorem is that it gives a general formulation that doesn't specify anything about order or the particular form of the Archimedean axiom. As usual, let L be an elementary language, and let the collection psi sub n for n a positive integer be a set of formulas of L. An example would be the ordinary formulation, which I've stated here in numerical terms. If x is greater than y, then n replicas of y for some n will be equal to or greater than x. So psi sub n would simply say, if x greater than y, then y combined with y n times equal to or greater than x. That'd be the form of psi sub n. And the general Archimedean axiom could be formulated using that is, for every x and for every y, there exists an n psi sub n. Notice, there exists an n catches the familiar property of quantifying over the positive integers in stating the Archimedean axiom. Now, let phi be a non-elementary formula, which will be of the form there exists an n phi n, psi n, as down there. And we want to say now that a model A of the language L satisfies phi if and only if A satisfies at least one sentence or formula of the form of the set psi sub n in and in. That's just spelling out in an explicit way what we mean for a model of the language to satisfy a non-elementary formula. Notice phi, you see, is not elementary because there's quantification over n. But all the sentences in the set psi sub n, in and in, all of these formulas or sentences are elementary. So we've used that to characterize what it means for a model A of L to satisfy phi. The intuitive idea is quite straightforward. Now the critical definition of an Archimedean theory. Let S be any set of sentences of L. Now those, of course, will be elementary sentences. Then we say that the pair S phi, where phi is of the form just discussed, the pair S phi is an Archimedean theory if and only if the following two conditions are satisfied. Every model of S and phi, that is, every model in which S and phi are satisfied of L, is embeddable in a numerical model of L. And secondly, no model of S and the negation of phi is so embeddable. And it's having phi and then not satisfied by the negation of phi that gives it the Archimedean character. The theorem that can then be proved with such a general characterization of Archimedean theory, and I think the great virtue of Néron's formulation is the generality of the formulation. The theorem that can be proved is this. Let S and phi be an Archimedean theory as just defined. Then there is no set of sentences of L whose models are exactly those of S phi. Another way of putting it is that the Archimedean theory S phi is not axiomatizable in L, period. That is, we could not have any set of elementary sentences of L that will serve as axioms. And that shows how powerful the Archimedean axiom is. We've now, in two different theorems, gotten these very general negative results about expressing as the Archimedean axiom within the framework of elementary theories. And I think where we come out on this is that in the investigation of axiomatizability problems, because most of the logical results apply to elementary theories, there are only a few scattered results that would be applicable and possibly would have some interest in theories of measurement for languages that are not elementary. Because of this fact and these very general results about the Archimedean axioms, when we consider theories of measurement, we are pretty much restricted in terms of interest to finitary theories of measurement. And as you will note, the real results special to theories of measurement we've concentrated on in this chapter and in this second lecture are finitary theories of measurement structures. We do have surprising results, surprisingly negative results. These surprising negative results show that the structure of finitary classes of measurement structures, the structure is more complicated than we might intuitively think before any investigation was made. At the same time, we do have some positive simple results about finitary classes of measurement structures, namely those that are severely restricted by some intuitive principle of symmetry, as in the case of equal spacing for different structures or extensive structures. Now, in this lecture and the preceding one on axiomatizability, we have certainly not had the opportunity to give a full coverage of the logical matters that are at the heart of the results. I do hope that we've been able, in the short period of 2 hours, to give you a sense of the kind of results that can be obtained using results from logic, and these results will have for you some intuitive content. To get a deeper appreciation of the results, it will almost be necessary to first spend some time in the literature of logic that is not relevant to the other chapters of volumes 1 and 2.